Hello students, I welcome you to my first lecture on the new topic thermodynamics, which is given as unit number 5 of class 11 chemistry. In today's lecture, we will discuss about thermodynamic terms and applications. Before that, I will just give an introduction of thermodynamics in brief. Chemical energy stored by molecules can be released as heat during chemical reactions when a fuel like methane, cooking gas, or coal burns in air. The chemical energy may also be used to do mechanical work when a fuel burns in an engine or to provide electrical energy through a galvanic cell like dry cell. Thus, various forms of energy are interrelated and under certain conditions, these may be transformed from one form to another. The study of these energy transformations forms the subject matter of thermodynamics. The laws of thermodynamics deal with energy changes of macroscopic systems involving a large number of molecules rather than microscopic systems containing a few molecules. Thermodynamics is not concerned about how and what rate these energy transformations are carried out, but it is based on initial and final states of a system undergoing the change. Laws of thermodynamics apply only when a system is in equilibrium or moves from one equilibrium state to another equilibrium state. Macroscopic properties like pressure, temperature do not change with time for a system in equilibrium state. We are going to study about many more things in this unit number 5 in different videos. I welcome you once again for this first lecture. Please note down all the important points. Thermodynamic terms. We are interested in chemical reactions and the energy changes accompanying them. For this, we need to know certain thermodynamic terms. These are discussed in this section. The system and the surroundings. A system in thermodynamics refers to that part of universe in which observations are made and remaining universe constitute the surroundings. So, system in thermodynamics refers to that part of the universe in which observations are made and the remaining universe constitute the surroundings. The surroundings include everything other than the system under consideration. System and the surroundings together constitute universe. Please see the figure. The figure 1 shows the system and the surroundings. Hence, universe is equal to systems plus surrounding. In the beaker, we have two chemical reactions A plus B that forms a system, and everything other than that is the surrounding. The system may also be defined by physical boundaries like beaker. Here beaker and a test tube or a system may be simply defined by a set of Cartesian coordinates specifying a particular volume in space, which is shown in the figure containing A plus B elements or compounds. It is necessary to think of the system as separated from surroundings by some sort of wall, which may be real or imaginary. The wall that separates the system from surroundings is called boundary. Types of thermodynamic systems. The systems may further be classified according to the movements of matter and energy in or out of the system. Open system. In an open system, there is an exchange of energy and matter between the system and the surroundings. Please see the figure above. In the open system, you can see that there is an exchange of energy and matter. So for example, heat energy is flowing into the system and it is also going out of the system. So liquid is a matter and there are the surroundings and the system is separated by conducting walls through which heat can flow into or out of the system. So this is called open system. Here the boundary as an imaginary surface enclosing the vessel and the reactants. The reactants are inside the container, inside the vessel. Closed system. A closed system is shown in the mid part of the diagram on the screen. Here in a closed system, there is no exchange of matter, but exchange of energy is possible. So it is an enclosed closed system. Here exchange of energy, heat energy going out or flowing into is possible, and the conducting wall there is no scope for or possibility of exchange of matter. There is no exchange of matter. The presence of reactants in an enclosed vessel made of conducting material. Example, if the container is made of copper or steel, heat can easily flow outside or flow into the system. This is a classic example of a closed system. The third system is an isolated system, which is shown in the right hand side, extreme right hand side of the figure on the screen. In an isolated system, there is no exchange of energy or matter. So, exchange of energy is zero, exchange of matter is zero between the system and the surroundings. The presence of reactants in a thermos flask or any other closed insulated vessel is an example of an isolated system. So we in this section we have learnt about an open system, closed system as well as isolated system. Thermodynamic state of a system. We describe the state of a system by its measurable properties. For example, we can describe the state of a gas by specifying its pressure, volume, temperature, etc. These variable properties are called state variables or state function. To repeat, a thermodynamic state is the condition of a system as specified by its physical properties. Properties such as pressure, volume, and temperature are called state variables or state functions because their values depend on the state of the system and not on how it is reached. State functions, the thermodynamic parameters which depend only on the initial and final states of system are known as state functions. Examples are internal energy, capital E, enthalpy, capital H, entropy, capital S, and Gibbs free energy, capital G. Path functions, the thermodynamic parameter where value does not depend merely on initial and final state but also on the path followed is known as path function. So path functions depend on the values of initial and final state but also on the path followed. Examples are heat and work done. Heat is represented by symbol small q and work done by W. Extensive properties. The properties which depend on mass of the substance is known as extensive properties. Such properties are mass, volume, internal energy, and enthalpy. Intensive properties. The properties which are independent of the mass of the system are known as intensive properties, that is temperature, pressure, density and refractive index, which do not depend on mass. These are called intensive properties. Then we have reactions, two types of reaction. First is exothermic reaction. Exothermic reactions are those reactions which proceed with the evolution of the heat. That means there is a transfer of heat. Transfer. Endothermic reactions are those reactions which proceed with the absorption of heat from the surroundings. Then there are some certain sign conventions which you should know. The heat absorbed by the system is taken as a positive. When the heat is evolved by the system, it is negative. When work is done on the system, it is positive, and when the work is done by the system, it is negative. Types of thermodynamic processes. If you want to raise the temperature of a system, we may do it by heating. This heating is called the process. The method of bringing about a change in state is called process. Example is heating. We have different types of processes like isothermal process, adiabatic process, reversible and irreversible processes. First, isothermal process. When the temperature of the system remains constant during various operations, then the process is called isothermal process. So hence, in the case of isothermal process, there is no change in temperature. That is, temperature remains constant. This is attained either by removing the heat or this from the system or by supplying the heat to the system, thus maintaining the temperature constant. Adiabatic process. In an adiabatic process, there is no exchange of heat between the system and the surrounding. Thus, in adiabatic process, there is always a change in the temperature. So, no heat is supplied from outside, and the process, the constant, there is always change in temperature due to internal reactions. Reversible process. In a reversible process, the initial and final states are connected through a succession of equilibrium state. Please note the word equilibrium state. So, reversible process, the initial and final states are connected through succession of equilibrium states. All changes occurring during the process are exactly reversed when it is carried out in the opposite direction. So, all the changes can be reversed in the case of reversible process. Thus, both the system and its surrounding must be restored exactly to their original state when the process has been performed and then reversed. Reversible processes are those processes in which the changes are carried out so slowly, please underline, so slowly that the system and surroundings are always in equilibrium. Irreversible process. The evaporation or condensation rapid by the sudden decrease or increase in the external pressure will lead to non-uniformity in temperature and pressure within the system, due to which the equilibrium will be disturbed. Such processes are called irreversible process. So please see the figure shown. This is an adiabatic process. The container, the transfer of heat is zero. So whatever reaction takes place, it is within the container or the vessel. This is adiabatic adiabatic process, where there is no transfer of heat from outside, and whatever temperature changes occur due to internal processes only. Internal energy as a state function. In chemical system, We have different types of energies like chemical energy, electrical energy, mechanical energy, or any other type of energy. We represent the total energy of system as internal energy, represented by the symbol capital U of the system. This internal energy may change when heat is supplied into or taken out of the system. Work is done on the system or by the system, and matter enters or leaves the system. So, various changes are possible, that is, changes in heat supplied, or change in work done, or changes in matter entering or leaving the system. First, we will take up the case of work. So, in the initial state of system A, let the temperature be TA. The internal energy of the system in the state of this system A will be UA. We can change the state of the system in two different ways. What are those systems? That is mechanical work. We can do mechanical work or electrical work. So when we do the mechanical work, a new state B and its temperature change is new temperature will be TB. Hence, so when we do the mechanical work, TB temperature increases, which is TB is greater than TA. TA is the old state, previous state, and TB is the new state. And the change in temperature is given by the relation, represented by the relation delta T. Delta T is equal to the difference of new temperature minus the old temperature. That is, delta T is equal to TB minus TA. Let the internal energy of the system in the state B be UB, and this change in internal energy is delta U is equal to UB minus UA. UB is for state B, internal energy in state B, and UA is in previous state. So therefore delta U, the change in internal energy is delta U is equal to UB minus UA. We can also change the temperature by doing electrical work. Say previous case, while mechanical work we do the work 1 kilojoules of work is done. Even in this electrical case also, if we do 1 kilojoules of electrical work by immersion of heating rod or any other thing which results in change in temperature, the change in temperature, say for this case it is TB minus A. For the same quantity of work done, the difference between the two temperatures will be same. That is, TB minus TA will be equal to delta T is same for both the cases. That is mechanical work and electrical work. J.P. Joule, who lived between 1840 to 18 who during the period 1840 to 1850 was able to show that a given amount of work done on the system produces the same change of state as measured by change in temperature of the system, irrespective of the path. Here, the path can be mechanical work or it can be electrical work, but the change is same. The state of change of state is same. The internal energy of a system can be achieved either by heat or by doing mechanical work. When internal energy of a system is changed by transfer of heat from surrounding to the system or vice versa without doing the work, then the exchange of energy results due to temperature or difference, and it is represented by letter Q, small q, and called heat. Consider bringing about the same change of temperature by transfer of heat through thermally conducting walls. So, transfer of heat can be affected by using thermally conducting walls instead of adiabatic walls. So, the heat absorbed by the system can be represented by letter Q and measured in terms of temperature difference TA and TB. The change in internal energy delta Q, that is TA minus TB, equals Q when no work is done at constant volume. In the case of other, when work is done, the change of state is brought out by both doing the work as well as transfer of heat, and it can be represented by equation delta U is equal to Q plus W, where delta U is the change in internal energy that is given by heat as well as work done. Heat is Q and W is the work done. However, delta U will depend only on initial and final state. It will be independent of the way the changes are carried out. If there is no transfer of energy as heat or as work, that is isolated system, that is if W equal to 0, Q equal to 0, then delta U equal to 0 in equation 1. Thus, equation 1, delta U is equal to Q plus W is the mathematical statement of the first law of thermodynamics, which states that the energy of an isolated system is constant. It is commonly stated as the law of conservation of energy. That is, energy can neither be created nor destroyed. Let us solve a question, a problem. Question 1. Express the change in internal energy of a system when no heat is absorbed by the system from surroundings, but work is done on the system. What types of wall does the system have? So first case is no heat is absorbed by the system from surroundings, but work is done on the system. In this case, delta U is equal to W adiabatic because no heat is transferred. So the wall is adiabatic. Part 2 is no work is done on the system, but Q amount of heat is taken out from the system and given to the surrounding. What type of wall does the system have? So for part 2, we know that the heat is taken out from the system. So it is minus Q. Delta U is equal to minus Q. This is thermally conducting walls like copper or aluminum, etc. Part 3. W amount of work is done by the system and Q amount of heat is supplied to the system. What type of systems it would be? So using the relation delta U is equal to Q minus W because work is done by the W is minus because work is done by the system. Therefore, it is a closed system. Please note that the value of volume of a system is measurable, whereas the absolute value of internal energy U cannot be measured, but we can always measure the changes in internal energy. That is, delta U of the system can be measured. Applications. Many chemical reactions involve the generation of gases capable of doing mechanical work or the generation of heat. It is important for us to quantify these changes and relate them to the changes in internal energy. In this application parts, we will carry out many mathematical representation to explain the properties and state of thermodynamics. Consider a cylinder which contains 1 mole of an ideal gas fitted with frictionless piston. The total volume of gas is Vi and pressure of the gas inside is P. So initial Initial volume is Vi and the pressure of the gas is P. If external pressure Px here in this diagram is greater than P is the pressure inside, the piston is moved inward till the pressure inside is equal to the pressure outside. Let this change in volume. So when it is compressed, the new volume is final volume is Vf is represented by Vf. Due to this compression, the piston moves a distance L. So initially it was here and final position it is here, and the distance between the two positions Vi and Vf is shown here. And the graphical representation, initial volume is Vi here, pressure was more, and then final volume is shown here, and the graph is shown exponentially down. So PV plot, when pressure is not constant, the changes in infinite step reversible conditions during the compression from initial volume Vi to final volume Vf is shown in the diagram. Here the change is achieved in a single step and the final volume is Vf. During this compression, Vi to Vf, the piston moves a distance L and the cross section of this cylinder, this part of this is A. Then we can relate volume change is equal to Vf minus Vi, that is equal to L into A, that is equal to change in volume is delta V. But we know that pressure is equal to force per unit area or force per area. Therefore, force is given by pressure into area. Pressure here is external Px into A. Work done on this system is force into distance by definition. That is equal to force is Px into A and distance traveled by the piston is L. That can be written as Px into A into minus delta V, that is reduction volume, that is equal to minus Px into minus delta E, delta V. So because work is done on this system, Px is minus P. Therefore, minus into minus becomes plus. It is Pex into Vf minus Vi. Let it be equation 2. So the total work done on the system or on the gas is W is equal to, it is represented by sigma summation of all small squares P into delta V. That can be written mathematically in terms of integration, that is minus of sigma integral Vi to Vf of Pex dV. That is from the equation 2. Under reversible condition, equation 3 for work done can be related to internal pressure of the system as follows. So we can relate equation 3 to the internal pressure, that is W reversible will be equal to minus of integral Vi to Vf Pex into dV, that is equal to minus Vi to Vf P internal plus or minus dP into changes in, that is pressure, into dV. For all practical purposes, dP into dV is very small and we can write this equation, the above equation, as W reversible is equal to minus integral Vi to Vf into Pn into dV. Let it be equation 4. Applying ideal gas equation for n mole of gas, and using the gas equation PV is equal to nRT, we can write P is equal to nRT divided by V, and the same thing can be written for isothermal process, that is at constant temperature WREV reversible is equal to minus integral Vi to Vf of nRT, that is value of P in is nRT divided by V, and bracketing dV by V, we can write it as W reversible is equal to minus nRT, because n is constant, R is constant, and there is no change in temperature. T is also constant, and integral dV by V is natural log Vf by Vi. So substituting for natural log by log to base 10, we can write from our mathematical knowledge W reversible is equal to minus 2.303 into nRT log Vf by Vi, because we have natural log to base 10 is multiplier is 2.303. Let it be equation 5. We'll continue our discussions with the applications part of our video. In chemistry, we face problems that can be solved if we relate work term to internal pressure. So we are going to have derivations in terms of work and internal pressure of the system. So recall the equations which we derived in the previous slide, that is equation number 1, delta U is equal to Q plus W, that is change in internal energy is equal to quantity of heat plus work done. And the equation 2 is W is equal to PEX into Vf minus Vi. And the third equation we had derived in the previous slide is W is equal to minus integral Vi to Vf PEX dV, where PEX is the external pressure. We will use these three equations in our derivation. The problems part of this insert box I will discuss later. When PEX equal to 0, the expansion of the gas is called free expansion and no work is done. That is W is equal to 0 during free expansion of an ideal gas, whether the process is reversible or irreversible. Equation 1 may be written in number of ways. So put W is equal to minus PEX delta V is equal to 2 in equation 1. What is equation 1? Equation 1 is delta U is equal to Q plus W. Therefore, we can get delta U is equal to Q and minus PEX into V. Therefore, if the process is carried out at constant volume, delta V is equal to 0, then delta U is equal to QV. Because here delta V is 0, there is no change in volume. Then we will discuss isothermal and free expansion of case of an isothermal and free expansion of a gas. For isothermal, T is constant. Expansion of ideal gas into vacuum is equal to W is equal to 0 since PEX is equal to 0. Joule determined experimentally that Q equal to 0, that is transfer of heat is 0. Therefore, delta U is equal to 0. Equation 1 can be expressed for isothermal, irreversible and reversible changes as follows. So equation 1 is here. For isothermal irreversible change, Q is equal to minus W, because there is no change in temperature. Temperature is constant. Therefore, that is equal to PEX into Vf minus Vi. W is equal to PEX into Vf minus Vi. This is for isothermal irreversible change. For isothermal reversible change, Q is equal to minus W, that is equal to nRT natural log Vf by Vi. That is from equation number 5. That is equal to 2.303 nRT log of Vf by Vi. For adiabatic change, Q is equal to 0. Therefore, for delta U is equal to W adiabatic, because heat transfer is 0. Now we will take up the problem. Question number 2. 2 liters of an ideal gas at pressure of 10 atm expands isothermally at 25 degrees centigrade into vacuum until its total volume is 10 liters. How much heat is absorbed and how much work is done in the expansion? We know that for isothermal, Q is equal to minus W, that is equal to PEX into VI minus VF minus VI. So initial volume is 2 liters, final volume is 10 liters. Therefore, PEX into 10 minus 2, that is equal to PEX is 0, that becomes 0. So we have Q is equal to no work is done and no heat is absorbed. Question 3. Consider the same expansion, but this time it is against a constant external pressure of 1 atmosphere, 1 atm. Answer. We have Q is equal to minus W, that is equal to same formula PEX into 8. Here the value of PX is given as 1 atm. Therefore, Q is equal to 8 liters atm. Question 4. Consider the expansion given in question 2 for 1 mole of ideal gas conducted reversibly. We have to use the formula Q is equal to minus W, that is equal to minus 2.303 nRT into log Vf by Vs. Substituting the values, we know 2.3 into N is 1 mole. 1 mole is 1 and value of R is 0.8206 into log of into 98, 298. T value is 298, that is 273 plus 25 degrees into log of 10 by 2, that is the answer is 393.66 liter atm. Next we will take up the section 5.2.2, which is given in NCERT book, and its heading is enthalpy, represented by capital letter H. It is a bit lengthy section spread into the 5 slides in this video. So please listen very carefully. Section part A is a useful new state function, enthalpy. Enthalpy, the heat absorbed at constant volume, is equal to the change in internal energy. That is, change in internal energy is delta U is equal to Q subscript V. The subscript V represents the constant volume. That is, heat is absorbed at a constant volume. And the change in internal energy is equal to heat absorbed at constant volume. But most of the chemical reactions are carried out not at constant volume. The above equation is for constant volume, but under constant atmospheric pressure. So instead of constant volume, we have to focus on constant pressure. So we may write equation 1, that is delta U is equal to Q minus P into delta V, as delta U is equal to Q subscript P minus P into delta V. Here this process is under constant pressure, where Q subscript P is the heat absorbed by the system. This is the heat absorbed by the system, and minus this second term, minus P delta V, represents the expansion work done by the system. So heat absorbed does some work, and that is represented by minus P delta V. Let us represent initial state by 1, subscript 1, and final state by subscript 2. We can write this equation delta U as U2 minus U1 equals QP minus P into change in volume is V2 minus V1. By rearranging this equation, we can write it as QP is equal to U2 minus U2 plus P into V2 minus of U1 into P into V1. Let it be equation 6. Now we can define yet another thermodynamic function, enthalpy. Please underline, which is represented by letter capital H as H is equal to U plus PV. Let it be equation 6. So equation 6 becomes, that is equation 6 becomes H2. This term is H2 minus H1. This is H1 and this is H2. So therefore QP is equal to H2 minus H1, that is equal to delta H. Although Q is a path dependent function, H is a state function, that is enthalpy is a state function because it depends on U, P, pressure and volume, all of which are state function. Therefore delta H is independent path. So change in enthalpy is independent path, hence QP is also independent path. For finite changes at constant pressure, we can write equation 7 as delta H is equal to delta U plus delta P into V. Since P is constant, we can write this equation as delta H is equal to delta U plus P into delta V. This is the rearranging. It is important to note that when heat is absorbed by the system at constant pressure, we are actually measuring the changes in enthalpy. So this equation 8 is actually measuring the enthalpy. Remember, another point to remember is delta H is equal to QP, that is quantity of heat supplied at constant pressure, heat absorbed by the system at constant pressure, whereas delta H is negative for exothermic reactions which evolve heat during the reaction, and delta H is positive for endothermic reactions. So for exothermic, delta H is negative. For endothermic, delta H is positive. This you have to remember. Maybe you may be asked some objective type questions. So delta H is positive and it results in absorption of heat from the surrounding. We'll continue our discussions on enthalpy, that is capital H. At constant volume, that is change of volume is 0, delta U V is equal to 0. Therefore, recalling the equation number 8, that is the relationship delta H, change in enthalpy, is equal to delta U, change in internal energy, plus P into delta V. We can write this equation as delta H is equal to delta U into QV. This Q subscript V is the heat, change of heat at constant volume. The difference between delta H and delta U is significant when gases are involved. In case of solids and liquid, the difference is negligible, not significant. If VA is the total volume of gas reactants and VB is the total volume of products, so Na is the number of moles of gaseous reactants and Nb is the number of moles of gaseous products, all at constant pressure and temperature, then using the ideal gas equation, we can write P into Va is equal to NaRT, that is PV is equal to RT, NaRT, and P into Vb, that is for products, is equal to Nb into RT. So subtracting this equation from this, we can write this, combining these two, we can write P into Vb minus Va. P into Va is equal to Nb into RT minus Na into RT. Again, that we can write it as NB and minus NA, RT taking RT common, or P into VB minus VA equals NB minus NA into RT, or we can write VB minus VA is the delta V, that is equal to this, we can write it as NB minus NA is equal to delta NG into RT. Let it be equation 9. Here delta Ng refers to the number of moles of gaseous product minus the number of moles of gaseous reactants, that is Nb minus Na. Substituting the value of P delta V from equation 1 in equation 8, we can write delta H is equal to delta U. Delta H is equal to delta U plus delta NgRT. Let it be equation 10. The equation 10 is useful for calculating delta H and delta U and vice versa. So let us solve a problem. Question number 5. If water vapor is assumed to be a perfect gas, molar enthalpy change for vaporization of 1 mole of water at 1 bar and 100 degrees Celsius is 41 kilojoules per mole. Calculate the internal energy change when 1 mole of water is vaporized at 1 bar pressure and 100 degrees centigrade. Answer. Now here the change is water in liquid state to water in gaseous state. So therefore enthalpy H is equal to delta U, that is change in internal energy, plus delta Ng into RT, that is equation number 10 shown in the on the slide. Therefore we can write delta U is equal to delta H minus delta Ng RT. Therefore delta U is equal to, it is given substituting the values, change in enthalpy is 41 kilojoules per mole, it is given, and minus 1 into 8.3 joules per mole into temperature Kelvin is 373, that is 25 plus 273. No, sorry, this is 100 plus 273. That is that is RT, temperature in Kelvin, that is equal to 41.00 kilojoules per mole minus, simplifying this, multiplying this, 3.096 kilojoules per mole. So the answer is 37.904 kilojoules per mole. Next is extensive and intensive properties. The extensive property is a property whose value depends on the quantity or size of the matter present in the system. So extensive property is a function of quantity and size of the matter. For example, mass, volume, internal energy, enthalpy, heat, capacity, etc. are extensive properties. Those properties which do not depend on the quantity or size of the matter present are known as intensive properties. For example, temperature, density, pressure, etc. are intensive property. A molar property xm is the value of extensive property xi. This is also sometimes spoken as xi subscript m. So a molar property xi m is value of extensive property xi of the system for 1 mole of substance. This symbol is also called chi, chi, Greek word chi. So some books say xi and some books say chi. If n is the amount of matter, xi m is equal to xi by n is independent of the amount of matter. Other examples are molar volume, Vm and molar heat capacity Cm. From the figure, it is clear that volume is an intensive property and the temperature is an intensive property. Let us consider a gas Consider a gas enclosed in a container of volume V and temperature T as shown in figure A. Let us make the partition as shown in figure B. Now has one half of the original volume V by 2. Each part has got volume V by 2, but the temperature still remains the same. That is, temperature remains the same both in the left part as well as the right part as shown in the figure. It is clear that volume is a extensive property and temperature is an intensive property. Next is heat capacity. How to measure heat transferred to a system which appears as rise in temperature. The increase in temperature is proportional to heat transferred, and heat transferred is given by Q is equal to coefficient into delta T. Here, by replacing the proportionality constant with coefficient. This coefficient can be represented by the letter capital C. Hence, Q is equal to capital C into delta T. Coefficient C is called the heat capacity. The magnitude of coefficient depends on the size, composition and nature of the system. When C is large, a given amount of heat results in only small temperature rise because it is delta T. Water has a large heat capacity and lot of energy is required to rise its temperature. Capital C is directly proportional to the amount of the system. Therefore, molar heat of a system's capital C subscription Cm is equal to small c by n. So Cm is the heat capacity of the 1 mole of the substance and is the quantity of heat needed to raise the temperature of 1 mole by 1 degree Celsius or Kelvin, 1 Kelvin. Specific heat, also called as specific heat capacity, is the quantity of heat required to raise the temperature of 1 unit mass of substance by 1 degree Celsius, and it is represented. Specific heat capacity is represented by letter small c. For finding out the heat Q required to raise the temperatures of a sample, we multiply the specific heat of the substance small c by m mass and temperature change as Q is equal to specific heat mass into change in temperature. These are the from basic knowledge of physics. Therefore, that is equal to Q is equal to C into m is capital C and delta T. Let it be equation. Then the last one is the relationship between Cp, Cv for an ideal gas. At constant volume, capacity C is represented by C subscript V because volume is constant. And at constant pressure, this is represented by letter Cp. Let us find the relationship between Cp and Cv. Heat Q at constant volume is given by Qv is equal to Cv into delta T, that is equal to delta U. So heat at constant pressure Qp is equal to Cp into delta T, that is equal to delta H. Therefore, the difference between Cp and Cv can be derived from this ideal gas equation. For a mole of ideal gas, delta H is equal to delta U plus delta into P into V. That is equal to delta U plus delta into RT. That is delta U plus R into delta T. Therefore, delta H is equal to delta U plus R into delta T. Let it be equation R into delta T. Substituting the values of delta H and delta U from the above equation, we can write Cp into delta T. The value of delta H is Cp into delta T from this equation, that is equal to delta U is Cv into delta T plus R into delta T. So delta T gets cancelled in left hand side as well as right hand side. We get Cp is equal to Cv plus R. Therefore, rearranging Cp minus Cv is equal to R. Now we will take up some multiple choice questions quickly. System in which there is no exchange of matter, work or energy from surrounding is, four options are given. So option A, closed system, adiabatic system, isolated system or isothermal system. You have to remember that. An isolated system, work, energy or heat are not exchanged with surroundings. Hence, the answer is C, isolated. Next question. When the system does not exchange heat with the surrounding, the process is, four options are given. You have to identify. Please read all the four options and mark your answer. Pause the video, mark your answer. I will give the correct answer. In adiabatic process, system does not exchange heat with the surrounding. Therefore, the correct answer is B. Please mark it. Delta U is equal to Q plus W is the equation for, you have to identify, four options are given. First law of thermodynamics, second law, third law and zeroth law of thermodynamics. You have to mark the correct answer. The correct answer is first law of thermodynamics. This is the equation for first law of thermodynamics. Next question. The work done during expansion of gas from 4 dm cube to 6 dm cube against a constant external pressure of 3 atm is, and given that 1 liter atm is equal to 101.32 joules. So four options are given. Please read all the four options and mark your answer. I will give the correct answer. So we have to make some calculation and use the equation. W is equal to minus Px into Vf minus Vi, where Px, W, Px and Vf are the standard terms explained earlier. So substituting the values, we get the answer as approximately equal to minus 608. This is given as option B. Please mark it. Next question. If W is the amount of work done by the system and Q is the amount of heat supplied to the system, identify the type of system. So please read the question once again. Read the four options. Isolated system, closed system, open system, system with thermally conducting walls. Explanation is, the Q amount of heat is utilized to do W work. Matter is not exchanged. Hence, the system is a closed system. Please mark answer B as the correct answer. Next question. A 5-liter cylinder containing 10 moles of oxygen gas at 27 degrees, due to sudden leakage through the hole, all the gas escaped into the atmosphere and the cylinder got empty. If the atmospheric pressure is 1 atmosphere, calculate the work done by the gas. Four options are given. Please pause the video, read the question and all the four options. I will give the explanation. It is given, you have to make use of certain formula. Vf is equal to nRT divided by P. Substituting the values of N, that is 10 moles, and constant value of R is 0.0821, and temperature T in Kelvin, that is given temperature 27 plus 273 is equal to 300 Kelvin, divided by P is 1 atmosphere. Substituting the value, we get as 246.3 liters. We also know delta V is equal to Vf minus Vi. So the volume is, new volume is, Vf is 246.3, original volume is given as 5. So the answer is 241.3 liters, and we have to use it in formula WEX is equal to minus P into A into V. So A into V is the total volume. Therefore, P is minus 1 into 241.3 liters ATM. Therefore, that is equal to the value of converting into joules. We get 241.3 into 101.3 joules. That is equal to 24443.7. This answer is given as option B. Please mark it. Next question. A process is called reversible when four options are given. You have to remember, read all the four options A, B, C, D and mark your answer. I will give the correct answer. A reversible process is slow change during operation. Surrounding is always in equilibrium with this system. This is given answer as option C. Next question. For an isothermal reversible expansion process, the value of Q can be calculated by the expression. Please read all the four options carefully. The difference is here positive, option B is negative, option C is minus nRT. Here the value of 2.30 is missing, and the difference here it is Q is equal to 2.30 into P external. So note down all the difference. Just recall your memory and remember that equation Q is equal to minus W is equal to 2.30 nRT into log of V2 by V1. This option is given as option A. Please mark it. Next question. Thermodynamics is not concerned about four options are given. Energy changes in chemical reaction, the extent to which a chemical reaction proceeds, the rate at which the reaction proceeds, and option D is feasibility of a chemical reaction. Thermodynamics, the explanation is thermodynamics is not concerned about how and what are rate chemical reactions are carried out, but it is based on the initial and final states of a system undergoing the change. This I had explained in the introductory part of this video. Please mark it. The correct option is the rate at which the reaction proceeds. Next question. The state of gas can be described by quoting the relationship between pressure, volume, temperature, temperature, amount, pressure, amount, volume, temperature, pressure, volume, temperature, and amount. Here in our equations, amount was represented by n moles. So the correct answer is you have to remember and mark it as D. Next question is delta U is equal to. So you have to fill up the blank. First one option is adiabatic work, isothermal work, isochoric work, and isobaric work. So the first law of thermodynamics says delta U is equal to Q plus W. This you have to remember. Change in internal energy. Therefore, for adiabatic process, Q equal to 0. Therefore, delta U is equal to work done. Therefore, you have to mark the correct answer as adiabatic. Next question. The volume of gas is reduced to half from its original volume. The specific heat will be reduced to half, option A, B doubled, remains constant, and option D is B increased 4 times. So the specific heat is an intensive property which does not depend on the quantity or size of the matter. Hence, option C is the correct answer. Please mark it. With this, we come to the end of the first lecture on thermodynamics. And in the next lecture, we will study about calorimetry and enthalpy changes. Till then, goodbye.